All right, silly people, here's the situation. We are just proving that the continuity equation holds for a system of a charged particle in an electric field. Um, Given that the form of the current density invariant under Gaines transformation is this thing, um, and we're proving this continuity equation. So I'm just going to do a little bit of a left-hand, right-hand proof. So starting with the left-hand term, we're doing the time derivative of the square modulus of the wave function, which is this time derivative of psi star psi, which is psi star del psi del t plus psi del psi star del t. Um, Using the Schrodinger equation, you can write IH bar del psi del t is equal to just h psi, and you can also take the complex conjugate of the Schrodinger equation like that, and then you can rewrite now del psi star, or del psi squared del t, as being it's going to be psi star times 1 over IH bar h psi, and that's the Hamiltonian, and then plus, or actually minus 1 over IH bar psi star Hamiltonian, and you actually have psi not star there and psi star here, right? So we can factor out a IH bar from this, and this is kind of what we're left with. Now, the first term, or I mean the second term, is just the complex conjugate of the first term, right? That's kind of how we derived it. So that means that we can rewrite it by multiplying it by 2I and just taking the imaginary part of the first term. So we're doing the imaginary part of psi star Hamiltonian psi. Okay, I wrote down the Hamiltonian for a reason, right? Let's look at it. It's 1 over 2m times that stuff plus q phi. Fantastic. Simplifying the prefactor a bit, we'll have 2 over h bar out front, and we're taking the imaginary component of 1 over 2m psi star p minus q over c a squared psi plus q phi psi star psi. Q phi isn't like an operator or anything, so you can just move the wave functions around like that, and it won't really even have an imaginary part of it at all. So going forward, we won't even worry about it. What is worth doing is expanding the square between the psi star psi and the other part, and factoring out 1 over 2m. So doing the imaginary part of psi star, and then in here we'll have p squared minus q over c p dot a minus q over c a dot p plus q squared over c squared a squared. psi. Okay. P squared and q squared over c squared a squared are both real quantities now, by definition. So we won't really consider them anymore. But it is worth now uh, expanding the definition of the momentum operator and simplifying the prefactor a bit. So you'll have 1 over mh bar, and then just pull out a q over c because that's all we're looking at now. The imaginary component of psi star, we have IH bar gradient of A plus IH bar A dot gradient psi. Okay, we can factor out an H bar, and now both of these terms are imaginary, so we can just knock the i's off. So you'll have Q over mh bar C times H bar times psi star divergence of A plus A dot gradient psi, and then the H bar gets canceled out. So you get this thing. And this is the form that I'm going to leave it in, and then do the right-hand part of the problem. So we need to prove that this is equal to negative the divergence of J, where J is given by this equation, the real part of that stuff in there. So just looking at this term, I can already tell that there's going to be some non-imaginary components. So I'm going to expand the definition of the momentum again, like that. And then the real part of that is the thing that doesn't have an I attached to it. So it's just the real part of minus QA over MC with psi star psi around it. So it's just minus Q over MC psi star A psi. And then taking the divergence of this now, we have minus Q over MC psi, or nabla dot psi star A psi. And then using a little bit of product rule, you can see that you have psi star divergence of A psi plus psi star A dot divergence psi, which is like the same thing that we got before actually, but with a minus sign on it. Psi star divergence of A plus A dot gradient psi. Does that match? Yeah, so this term is minus this term up here, which means we can write the continuity equation as being del psi squared del t plus divergence of J is equal to 0. Fancy.